Okay, this is for DCC or DC circuits 0.03, and it's number 76, which has 3 stars in the book. And so here is our circuit, which has a battery with 12 volts that goes into a parallel series of 1 resistor and 2 resistor, which their ohms are written here. Their resistance is written here. So, and then it goes into R4, R5, and R6 as a series. And then a capacitance, and then R3, and then another capacitor. Or capacitor and another capacitor. So this is the first capacitor, and this is the second. And so it does a lovely job of the problem gives you the numbers of each, which I wrote to the side here, as it would get really crowded on my circuit if I wrote them all out. And so it says in the problem, it says, assuming the circuit is connected to several or is connected for several minutes, calculate the current from the battery to each resistor, and then compute the magnitude of the charge of each plate of capacitors. And so, first, looking into the junction rule, we have, IN is going to equal I out. So I think that's where we should start, is with that knowledge. And then the REQ is going to be R1 and R2 are the only ones in parallel. So you're going to have the inverse of 1 over R1 plus 1 over R2. And then these ones are in series, 4, 5, and 6. So it's just going to be like that. You're just adding them together. And so what I did was REQ is I calculated that, which it's going to be R1 times R2 divided by R1 plus R2, because it's the inverse. And so that got me around 0.86. It was actually like 0.857. So I rounded up a little bit. And then this one gets me a nice clean number of 4.00 ohms. And so adding them together, you get 4.86. And so that is all of the resistance added together. And so then what you're going to do is you're going to put that into this equation, I equals V battery over R EQ. And so we know that the battery is 12 volts. And so we're going to do 12 volts divided by 4.86 ohms. And we get 2.5 amps. And so then because we have some that are in parallel and some that are in series, we have to do, I decided to tackle the parallel ones first. So I derived I1 plus I2 equals I being this. This is I. Oops, no. This is I, which we just figured out. So I equals 2.5. That's just the entirety. That's the current through the circuit. And so I1 plus I2 is going to equal I, because they're in parallel. And then we can also, we also know that I1 times R1 equals I2 times R2. And so I2 is going to equal I times R1 divided by R1 plus R2. And so we're looking for, because I decided to look for I2. And I could have looked for I1, but I just chose I2. And so 2.5 amps is I. So we're just plugging in this number, which we just derived. And then we're going to times that by 2.0 ohms, because that's what R1 was. It was given to us. And then we're going to divide that by 2 ohms plus 1.5 ohms, and we get 1.4 amps. So that equals I2. And so that gives us 1 currents going through our R2. And so then we're going to plug that into our other equation, this one right here, the top one. And so we have I1 plus 1.4 amps equals 2.5 amps, which we get I1 equaling 1.1 amps. So now we know the current between R1 and R2 based on the junction rule. We get that. So 1.4 and 1.1. So we now know for those in parallel. I'm just going to put a check mark by it. So then we want to find R4, R5, and R6. And so because they're in series, they're just going to equal 2.5 amps, which we already got here because they're in series. And then the R3 is after a capacitance. And so based on our knowledge that the circuit was connected for several minutes, we can assume, due to several minutes, that this is building up current right here, and so it is no longer flowing into R3. And so R3 is not getting any current through it. And so based on that knowledge, we're going to say I3 is equal to 0 amps. So we now have found I1, I2, I3, I4, I5, and I6. So we have now solved the first part of this problem, which was finding the current flowing from the battery to each resistor. And we use the junction rule as well as our knowledge of capacitors. And so the next part asks us to compute the magnitude of the charge on each plate of capacitors. And so we know this equation, Q equals C times V, and hopefully it's okay. And so then we also know that V is equal to I times R, which we could get from rearranging this equation up here. And so based on that knowledge, we can then say C times I times R, and we're doing it for the first resistor. And so it says micro farads. So we're going to have to do we're doing it on the capacitor, the first capacitor. That's what I meant. Oh, hopefully, maybe I shouldn't do it at an angle. And so we're looking for the charge on this capacitor. And so we know that 20 times 10 to the negative 6 farads is, because we have to make it into just farads rather than microfarads. And then we got I1 being 1.1 amps times R1, which was 2.0 ohms. And so that's how we're going to find the charge. And so I'm going to 20 times 10 to the negative 6 times 1.1 times 2. And wow, we get, equals 4.4 times 10 to the negative 5. Sorry. Gee whiz. Negative 5 coulombs, because we're doing charge. And farads times amps times ohms is coulombs. Okay. So we have figured out the charge distributed over the magnitude, or Sorry, I can't talk. We have computed the charge going over the capacitor of this guy right here. And so then we can then find the charge going over C2V2. And so because it's a lot different because, so these ones, the capacitor and the R1 are in parallel. But for this one, we're looking at a series with R4, R5, and R6. And so it's going to be a little different in that it's going to be C2 times, I times, and series R, oops, I don't know why I said R1. It's going to be R 4 plus R5 and plus R6. And so C2 is 40 microfarads. So that's going to be 40 times 10 to the negative 6 farads times I, which was 2.5 amps, times R4, which was 1 ohm, plus R5, which was 2 ohms, and then R6, which was 1 ohm. Not too bad. And so we're going to need to calculate. So that's 1, 2, 3, 4 ohms. Okay, so 4 times 2.5 is 10, right? 2.5 times 40 times 10 to the negative 6 farads. Okay. So, that's times 40 times 10 to the negative 6. So we get 4 times 10 to the negative 4, I think. Right? 1, 2, yeah, 4 coulombs. And so, yeah. So then that gets us the charge for the capacitor Q2. So we have figured out all parts of this problem, which was rather long.